Hello, everyone. So last time we looked at the derivative and derivative rules, the rules that help us calculate derivative of any given function without having to, calculate the limit definition of derivative, limit of the fraction f of x plus h minus f of x over h. So calculating that limit could be lengthy in some cases. So we want to derive some rules that help us calculate derivative of any given function, basically, quickly and easily. So last time, derivative rules. So the very first rule that we covered last time was that if you have a constant function, then we can say that f prime of x is equal to 0. So derivative of a constant function is 0. So this is also consistent with the concept of slope of tangent line. If you have a constant function, means you have a horizontal line, and then slope of tangent line will be 0 because a slope of a horizontal line is 0. Now the second rule we want to look at, if you have a function of the formula f of x equals x to power m, then the derivative of this function will be of the form mx to power m minus 1. So for now, let's assume for m in n. So let's assume m is a natural number for now, like 1, 2, 3, and so on. But later we will generalize this to any real number m. So this rule is basically valid for any real number m. But for the proof of any real number m, we can do it later. But for now, we'll do the proof for natural number m. So proof. So what will be f prime of x? If f of x is x to power m, then f prime of x will be limit f of x plus h minus f of x over h as h approaches to 0. And then this is equal to the limit h approaches to 0, x plus h to power m minus x to power m divided by h. Right? Because f of x is x to power m, so f of x plus h will be x plus h to power m. And then this is limit x to power m plus, so we are going to expand this, so x to power m plus m x to power m minus 1 h plus, m choose 2 x to power m minus 2 h squared. Maybe I don't have enough space here. Maybe I can write at the beginning of the line here. Limit x to power m plus m x to power m minus 1 h plus m choose 2 x to power m minus 2 h squared plus dot 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 all the way to last term is h to power m, and then minus x to power m divided by h approaches to 0. Here we use the identity, the binomial expansion. Do you remember about the binomial expansion? We used a plus b to power n. Like the special case is a plus b to power 2, which is a squared plus 2ab plus b squared. Now the generalization for that is called binomial expansion. And a plus b to power n can be written as a to power n plus n a to power n minus 1 b, n choose 2 a to power n minus 2b squared, dot 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 all the way to n choose n minus 1 a b to power n minus 1, and then finally b to power n. So this is the binomial expansion. Now, if you set n equals 2, then you get a plus b to power 2. And these numbers here, n choose 2, n choose n minus 1. So these are called combinations or binomial coefficients. And the formula is this. So n choose k is n factorial over k factorial times n minus k factorial. And n factorial, I suppose you mean, you know that n factorial means what? Means 1 times 2 times 3 times all the way to n. So 2 factorial, for example, is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24, and so on. So n factorial over k factorial times n minus k factorial, that's n choose k. And this is the expansion of a plus b to power n. So we use this identity. My a here is x, my b is h. So we use this, we wrote it this way. And then this will be equal to, now x to power m cancels with x to power m, right? So we are left with limit h approaches to 0. And then I can factor h out, h times m x to power m minus 1 plus m choose 2 x to power m minus 2h plus plus h to power m minus 1 divided by h. Now h cancels with h, and we are left with m x to power m minus 1 plus limit h approaches to 0. See, the limit is over h. So x is considered as a constant here. I can take take it out of the limit. So plus limit h approaches to 0. Now from the rest of the terms, again, I can take h out. So h common factor. And then what will be left? Like m choose 2. Yeah, I can take h out. So m choose 2. X to power m minus 2 all the way to h to power m minus 2. I'm taking one, or I don't have to take h out, just simply replace m with h. I can also do that. Just simply replace, say, m choose 2 x to power m minus 2h plus all the way to h to power m minus 1. Now h approaches to 0. As h approaches to 0, this will go to 0 and this will go to 0, right? Because 0 times anything is 0. So we are left with just mx to power m minus 1, which is what we wanted to show. So we showed that if f of x is x to power m, then f prime of x is equal to m x to power m minus 1. So for example, let's say let y equals x to power 5. Find dy to dx. See, sometimes in some questions, you may be asked to calculate, y prime or f prime of x. In some questions, you may be asked to find dy to dx. So dy to dx is another notation for y prime. Okay, so here again, so like I said, dy to dx is like the Leibniz notation for y prime. So we want to find y prime. We already know a formula for y prime. So here basically m is equal to 5, right? And so y is equal to x to power 5. So dy to dx, which is same as y prime, will be equal to 5 times x to power 4. Okay. All right, so that's another important differentiation rule, derivative of functions of the form x to power m. Now, the third rule for differentiation, let's say if you have a c f of x derivative, this is c times f prime of x. So if you have a constant multiplication of a function and you want to differentiate it, you can take the constant out. So let's see why. So proof, again, that g of x equals c times f of x, right? Then we want to find g prime of x, right? So the goal is to find g prime of x, right? So if you can show that g prime of x is c times f prime of x, so that's all we need to show. So how can I find g prime of x? G prime of x is equal to limit g of x plus h minus g of x over h as h approaches to 0. And then this is limit c times f of x plus h minus c times f of x divided by h. H approaches to 0. And then I can take c out. C times limit f of x plus h minus f of x over h. H approaches to 0, right? Because c is a common factor, I can take it out. And I can also take it out of the limit because limit is over h, right? So, and if you have a limit of a constant times the function, of course, you can take the constant out according to the limit rules. So this one basically it's by, if you have limit, let's say, for example, c times f of x as x approaches to a, for example, this one we can always say c times limit f of x as x approaches to a. And then this is equal to c times f prime of x. Right, because limit f of x plus h minus f of x over h is f prime of x. So I can replace it with f prime of x, and the answer will be c times f prime of x. Okay, so that's it. So we showed, if g of x is equal to c times f of x, then g prime of x is equal to c times f prime of x. So the constant always can be taken out. So for example, let's say if you have y equals 2x to power 5, then dy to dx can be written as 2 times d to dx of x to power 5, right? So 2 is a constant, can be taken out, and then differentiate the function inside. The function inside is x to power 5. So then that will be 2 times 5 times x to power 4, right? Because x to power m derivative is mx to power m minus 1. And then this will be 10 times x to power 4. X to power m derivative is mx to power m minus 1. So x to power 5 derivative is 5x to power 4. And then 2 times that will be 10x to power 4. Okay, so another derivative rule, the fourth one. Let's say if you have let f of x and g of x be differentiable functions, then f of x plus g of x is differentiable and the derivative of addition of two functions is simply addition of the derivatives. So f of x plus g of x derivative is equal to f prime of x plus g prime of x. The derivative of addition is simply addition of derivatives. Okay, so for proof of this, let me leave as exercise, very simple proof. I already did few proofs. So let me leave this one as exercise. It's very simple. So if you want to prove this, you can call f of x plus g of x. You can call it, for example, h of x. If you set h of x to be f of x plus g of x, then you want to find h prime of x. And you can show that h prime of x is f prime of x plus g prime of x. Okay, so let's look at an example. Let y equals 2x to power 6 plus 5x to power 4. Find dy to dx. So dy to dx, because you see we have addition of two functions, and we know that derivative of addition is addition of derivatives. So dy to dx is d to dx of 2x to power 6 plus d to dx of 5x to power 4. And this one is a constant, can be taken out. So 2 times 6 times x to power 5 plus 5 times 4 times x to power 3, right? So 2 can be taken out, derivative of x to power 6. We know that derivative of x to power m is mx to power m minus 1. So this is 6x to power 5. And derivative of x to power 4 is, again, using the same derivative rule. I can write it as 4 times x to power 3. So once we make these substitutions, we will get 12 x to power 5 plus 20 x to power 3. Okay, so this is the third rule. Now, another rule, let's say rule number 5. Again, let f of x and g of x be differentiable functions. Then we can say f of x times g of x is differentiable and the derivative of f of x times g of x can be written as f prime of x times g of x plus f of x times g prime of x. Derivative of product of two functions. So derivative of product of two functions is not like the product of derivatives. Okay, so f of x times g of x derivative is not same as f prime of x times g prime of x. So I can give you a important note or warning. F of x times g of x derivative is not same as f prime of x times g prime of x. Derivative of product is not same as product of derivatives. For addition, we had derivative of addition was same as addition of derivatives. But for product, no. Derivative of product is not product of derivatives. What is it? It's f prime times g plus f of x times g prime. Derivative of first function times second function plus derivative of second function times the first function. So that's the derivative of product of two functions. So another notation, sometimes this is used with another notation or more abbreviated notation, or let me say shorter notation. So this is called product rule. Because it's a rule for differentiation or derivative of product of two functions. So that's why it's called product rule. So shorter notation for product rule. Let's say if I said, let's say u equals f of x, and let's say v equals g of x, then what can we say? Then we can say that u times v derivative is equal to u prime v plus u v prime. See, if I call this one u, call this one v, u times v derivative is u prime times v plus u times v prime. So u times v derivative is equal to u prime v plus u v prime. So uv derivative is u prime v plus u v prime. So this one is maybe easier to memorize. It's just the same rule, but instead of f of x and g of x, we can call them u and v. Okay. So let's look at the proof first. Proof. And let's say let h of x, let's call f of x times g of x. Let's give it a name. For example, let's call it h of x. Then we want to find h prime of x, right? So want to find h prime of x. So h prime of x is what? H prime of x is equal to the limit h of x plus, we usually use h there, so let me call it t here because I used h for my function. So that's why I prefer not to write h of, we usually say f of x plus h, and h goes to 0. But here I called my function h. So let's say I write the limit. I use another letter here. So let's say t, for example. Limit h of x plus t minus h of x divided by t. T approaches to 0. And then this is equal to limit f of x plus t times g of x plus t minus f of x times g of x divided by t. T approaches to 0, right? See, we have a formula for h of x. It's f of x times g of x. So if I want h of x plus t, what should I do? I have to replace every x here by x plus t. So I will get f of x plus t times g of x plus t. And then minus h of x. H of x is again f of x times g of x. So I wrote it. And then divided by t. Now I have to simplify this because remember when you calculate a limit, you apply limit definition of derivative, you get always, if your calculation is correct, you get always something of the form 0 over 0. So if t goes to 0, I'll get f of x times g of x minus f of x times g of x, which is 0 over 0. And 0 over 0 means it's indeterminate and it has to be simplified, right? So how can we simplify this now? Because right now there is no common factor or something, right? Because it's f of x plus t, g of x plus t, and then f of x, g of x. So there is no common factor that I can take it out. So what can we do? So yes, there is no common factor, but I can do a trick and add and subtract a term. I'm going to add and subtract. So limit t goes to 0. And then I can say f of x plus t times g of x plus t minus f of x plus t times g of x plus f of x plus t times g of x. I don't have enough space, maybe. Sorry, just a little bit this side. F of x plus t times g of x plus t minus f of x plus t times g of x plus f of x plus t times g of x minus f of x times g of x divided by t. T approaches to 0. Okay, so I added and subtracted f of x plus t times g of x. So of course, I'm allowed to add and subtract a term or a number, because when you add and subtract the same term, that means you're adding 0 basically. And of course, I'm allowed to add 0 to my expression. It won't change it. But how does that help me? Because now I can take f of x plus t out. Between these two terms, I can take f of x plus t out. And between these two terms, I can take g of x out. So what will I get? I'll get limit f of x plus t. Let's take it out from the first two terms. Then what will be left? G of x plus t minus g of x divided by t. And then plus, so this is for the first two terms. For the first two terms here, I can take f of x plus t out. For the next two terms here, I can take g of x out. So plus g of x times f of x plus t minus f of x over t. And then this one, I can write it as, okay, see, I have limit of product of two functions. Limit of product of two functions is product of the limits as long as limit of each function exists. Well, this limit exists because g is assumed to be differentiable. So if g is differentiable, it means that limit g of x plus t minus g of x over t exists and is equal to g prime of x, right? So this limit exists. We have no problem with that. But what about the first term? Why does this limit exist? Can I say that limit f of x plus t as t approaches to 0 exists? Because I don't have any assumption about it. See? Remember, whenever you prove something in mathematics, of course, you can and you have to use the assumptions. You know, each theorem in mathematics has some assumptions and has some conclusions. Our job when we want to prove a theorem is to use the assumptions and you know, connect them or analyze them, and in order to prove or reach the conclusions. So here my assumption is that f of x and g of x are differentiable. So that's the only thing. And then my goal is to show that f of x times g of x is differentiable as well. And this is the formula for derivative of f of x times g of x. So my only assumption is that f of x and g of x are differentiable. So this limit exists because g is differentiable. But what about this limit? Limit f of x plus t. Why does this exist? So my claim is that this limit also exists. So this is limit f of x plus t. T approaches to 0 times limit t approaches to 0, g of x plus t minus g of x over t. So what is the reason? Since limit f of x plus t, t approaches to 0, which is same as limit. So if I call x plus t, let's call it, for example, some other letter. For example, let's say A or S. Let's call this one S. So then I can call it limit f of S. And S approaches to what? See, S is x plus t, and t approaches to 0. So as t approaches to 0, S will approach to x, right? So look at here, S is x plus t, t approaches to 0. So S approaches to x plus 0, which is x. So then this is limit f of s as s approaches to x. And this limit exists and is equal to f of x. Y is equal to f of x, so limit f of s as s approaches to x is equal to f of x by continuity of f. See, f is differentiable, right? So if f is differentiable, then f is continuous. We had a theorem before that every differentiable function is continuous. And if f is continuous, then limit f of s as s approaches to x, x exists and is equal to f of x. So by continuity of f, which has been concluded from differentiability of f. Yeah. Okay. The only assumption is that f is differentiable, but if f is differentiable, then it is continuous. And if f is continuous, limit f of s as s approaches to x must be equal to f of x. So this limit, since this limit exists, and limit, let me say, for example, g of x times h of x as x approaches to a is equal to limit g of x approaches to a times limit h of x. Okay, we don't have space here again. Maybe I can make this one a little bit smaller. So since this, and let me write this with limit of product of two functions is the product of limits if both limits exist. Okay, so this was a little bit long. Okay, so let me tell you the idea again. See, we have limit of product of two functions here. This is product of the limits of those two functions if we can justify that limit of each function exists. But limit of this limit exists by differentiability of g, which is my assumption. And this limit exists. Why? Because this limit, if we rewrite it this way, we can write it as limit f of s, s approaches to x, and this is equal to f of x. Because f is continuous. Why is it continuous? Because it's differentiable. It's assumed to be differentiable. And we know every differential function is continuous. So f is continuous. And if f is continuous, then limit f of s as s approaches to x is equal to f of x. This limit exists and is equal to f of x. This was the definition of continuity. Definition of continuity says that a function f is continuous, let's say at x, if limit f of s as s approaches to x exists and is equal to f of x. And here I know that f is differentiable, therefore continuous. Therefore, this limit exists and is equal to f of x. Therefore, both of these limits exist. Therefore, limit of product of these two functions is product of limit of those two functions. So this is for the first term. For the second term, it's more straightforward because g of x definitely can be taken out of limit. So this one is independent of t, and hence can be taken out of the limit. Right? This g of x is independent of t, so I can take it out of the limit because limit is over t, right? So anything that has no t in it is considered as a constant function and therefore can be taken out. So if I take this one out, I will have plus g of x times limit f of x plus t minus f of x over t as t approaches to 0. And now I'm ready to simplify further. So this limit, we already justified how much it is, right? Here I gave this reasoning in order to justify that I can write the limit of product as products or limits. But I can use the same reasoning to replace limit f of x plus t as t approaches to 0 with f of x, because this is exactly what I have justified here. I've justified that limit f of x plus t as t approaches to 0 is same as f of x. So this can be written as limit, and this can be written as f of x times, now what is this guy here? This guy is g prime of x, right? Because g prime of x, according to the definition, is limit g of x plus t minus g of x over t as t approaches to 0. So this guy here is g prime of x plus, what about this guy? So g of x times, and this guy is f prime of x, again, according to the definition. By definition, we know that f prime of x is limit f of x plus t minus f of x over t as t approaches to 0. So plus g of x times f prime of x. So we showed that f of x times g of x derivative is equal to f prime of x times g of x plus f of x times g prime of x. So let's look at an example now. Let y equals x times x squared plus 1 to power 2 let's say just x times x squared plus 1. Find dy to dx. So we can write two solutions. Solution 1, y is equal to x times x squared plus 1. So this is like, I can call this one u and call this one v. So u times v. What is the derivative of u times v? So then dy to dx is equal to, so we know that u times v derivative is u prime v plus uv prime. So this one is d So basically x derivative times x squared plus 1 plus x times x squared plus 1 derivative. Now derivative of x is 1, so 1 times x squared plus 1 plus x times, now what is derivative of x squared plus 1? Here we have addition of two functions, x squared and 1. So derivative of addition of two functions is addition of their derivatives. So the answer will be the derivative of x squared, which is 2x, plus derivative of 1, which is 0. Because derivative of constant function, we know it's 0. And we know derivative of x to power m is m times x to power m minus 1. So x times 2x. And then this is x squared plus 1 plus 2x squared. And the answer will be 3x squared plus 1. So this is one solution. And solution two, y, what is y? Y is x times x squared plus 1, right? So this is what the question says. I can expand this first. So if I expand this, I'll get x to power 3 plus x. Right? So x times x squared plus 1, if I expand it, it will be x to power 3 plus x. So what will be y prime then? So y prime equals dy to dx will be derivative of x cubed plus derivative of x. Derivative of addition of two functions, addition of the derivative. So derivative of x cubed plus derivative of x. Derivative of x cubed is 3x squared. Derivative of x is 1. So 3x squared plus 1. Which is consistent with the answer we got above. All right. So the next rule, so the fifth rule, this was rule number, so this was fifth rule. So sixth rule, quotient rule. So we learned how to calculate derivative of product of two functions. Now we have to see how we can find derivative of division of two functions. So one function divided by another one. How can we find derivative of the resulting function? So let f of x and g of x again be differentiable functions. And let g of x to be g of x not equal to 0, right? Why should I assume g of x not equal to 0? Because I'm going to consider f of x divided by g of x. So of course, denominator has to be non-zero. So that's why I'm assuming that g of x is not 0. Then f of x over g of x is differentiable and f of x over g of x derivative is equal to f prime of x times g of x minus f of x times g prime of x divided by g of x the whole squared. So in U and V notation, in U and V notation, we can set again U equals f of x and V equals g of x. then we can say that u over v derivative is equal to u prime v minus u v prime divided by v squared. U over v derivative is equal to u prime v minus u v prime over v squared. Okay, so again, derivative of division of two functions is not simply division of derivatives. F over g prime is not f prime over g prime, or in u and v notation, u over v prime is not u prime over v prime. What is it? It's u prime v minus u v prime divided by v squared.